welcome back. In this lecture, we are going to describe molecular interaction in dense fluid media. So, if you recall, we looked into the different potential models in the last few lectures. However, they were kind of potential models in vacuum. Okay, that means essentially when we consider two particles coming from very far, okay, only two particles, what would be the typical kind of potential energy? So, we described using different kind of potential models such as Coeval, Lennard-Jones models, Sutherland, exponential C, Kihara and so forth. But in the solution, when you bring two particles or two, let us say, solute closer to each other, it has to also experience solvent interaction. In other words, it must repel the solvent molecules in order to come closer. Okay, thus the kind of effective interaction between the solute may not be the same as that seen in the case of the vacuum. Okay, so let me just draw the typical interaction which we know when you, it's like a Lennard-Jones. Okay, when you bring one particle I and particle j, okay, from very far, okay, from let us say distance r, okay, where r can vary from infinity to somewhere near the molecular size. So, this is a typical interaction or intermolecular potential for low dense gas. So, essentially for the low dense gas system, when you bring the two particles close enough, they typically do not experience other molecules present in the system because they are extremely far because of extremely large volume. Okay, but in the case of solid molecules, in a liquid solvent, it interacts with the solvent molecules. So, molecules. So, in this case, how do you present the effective interaction between two solid molecules? So, we typically represent this kind of effective interaction between two solvent molecules in a solvent medium by something we call it potential of mean force. So, the interaction between two molecules is described by two molecules in a solvent is described by potential of mean force. It's called sometimes PMF also. So, remember, like in vacuum or low dense gas medium, the two particle interaction can be described by potential models such as Lennard-Jones, which I have drawn here. But in case of a solvent molecules present in the system, the two particle interaction will be represented by something called potential of mean force. Now, this plays a very important role. So, it's important, this potential of mean force is important in colloidal science, and physical chemistry of protein solution, okay. Now, this potential of mean force incorporates the nature of the solvent. What does it mean? That if you change the solvent and you keep the solute fixed, the effective interaction between the solute will also change. Okay, so that means the nature of the solvent will affect the potential of mean force or intermolecular interaction between the solute. Let us try to understand a little more schematically this concept. So, let me just draw kind of a solvent molecules like this sphere. Okay. Now let us say this is one solute and this is another solute. Now in order to this solute to come closer, okay, when you bringing this close enough, it must repel this blue circles. Okay. Now effective solute-solute interaction now includes a direct solute, so this will be direct solute-solute interaction, and as well as any changes in solvent and solute, solvent and solute, and solvent and solvent, okay, during the approach. Okay. So effective solute-solute interaction will have all this contribution. Now let us consider a case like you have a solute which typically is attractive to each other in vacuum. So when you bring it closer, it can be represented by simple Lennard-Jones potential, okay, which has a minima, essentially means that another solute will try to approach to the minimum value. Okay. Now consider the same solute in solvent. It can approach only after displacing solvent molecules, okay, which is the case if you consider this. For example, let us assume that you trying to keep this fixed and you bring it from here to here. In order to this to come here, you must displace this and this as well. Okay, so it should get it should displace in order to come closer. Now as I said that in free space, the solute-solute may be attractive, but now it is possible that they can repel. So while it is attractive in the free space, but when you consider the solvent and you try to bring it closer, it's also possible that the solute will repel, and the repulsion depends on two things. Okay, let me just write down that. That means they can repel each other in solvent if the work done to displace the solvent molecule is less is greater than the work done to displace the solvent molecule is greater than the energy gained by approaching solute. So what is this statement says that if the final state where the solute is close enough, that energy is less than the work which requires to bring the solute together or closer. In that case, the solute will not prefer to be close and they will repel. Okay, but for simple reason is that it will take more energy to bring in and the gain is much less. And we know the system prefers to have a minimum energy and thus they would not like to come. So a case where the solute are attractive in the free space will become repulsive in solvent. Okay, that is something which is a common case. Now in addition to that, the solute can perturb the solvent molecules and a local ordering of this. Now, due to that, there is another contribution which is basically the solvation force which may arise. Okay. Now, considering that the solvent can be of different type, which essentially means that molecular nature of solvent can have effective or can affect the potential of mean force or effective interaction between the solute significantly. So, that means molecular nature of solvent can produce PMF much different from the corresponding two body potential and two body potential in vacuum. Okay. So, this is something which is already clear in this discussion here. So, what is a PMF? PMF is nothing but the measure of intermolecular forces between the solute molecule in solvent. Okay. And this is something which is going to be different from the corresponding to the two body potential in vacuum. Okay. Now, this is why we are discussing this, because we would like to provide quantitative information of PMF and macroscopic thermodynamic property, which apparently many solution thermodynamics of many solution theories have looked into. So, for example, solution theory such as Macmillan Mayer theory it provides a direct quantitative relation between PMF and macroscopic thermodynamic property. So, what is this property? This property such as osmotic virial coefficient. Okay. And this is something which we can obtain using osmotic pressure measurements. Okay. So, now what I am going to do is I am going to describe this osmotic pressure. So, let me describe this osmotic pressure, and which is extremely useful for large molecules to evaluate their molecular weight and so forth. So, come to that very soon. So, what is this osmotic pressure? This before going into the details, this is something which is often encountered in nature. Okay, especially in biological systems. Okay. So, let me first draw a schematic representation where this osmotic pressure comes into consideration. So, let us consider a system okay, something like this, where you have this at pressure P, this is at pressure P plus pi, and this vessel, this could be a biological system, this is separated by semi permeable membrane. . which allows only solvent to pass through but does not allow the solute. Okay. So, let us consider the solvent here is 1, and so this is a solute plus solvent. So, this is a solution, okay, where you have 1 and 2, solute is 2, and it allows only 1 to pass. So, that means here you have 1. So, there are two phases here. So, this is phase alpha and this is phase beta, okay, and this is only solvent here. So, in such a case, the left hand side is at pressure P and the right hand side at pressure P plus additional term called pi, okay, which is basically nothing but the osmotic pressure. Now, I would like to come up with a relation of this pi with thermodynamic quantities such as temperature, pressure and concentration. So, that is the objectivity of this exercise here. Okay. Now, initially they may not be at equilibrium, but after a certain time it reaches an equilibrium, and then we can consider that at equilibrium you have a chemical equilibrium condition which you can evoke. Okay. So, mu 1, again we are looking at solvent is 1, solute is 2, alpha is phase, should be same as mu 1 beta. Okay. So, this tells you that the chemical potential of solvent in phase alpha should be same as chemical potential of solvent in phase beta. Now, the next thing which we need to do is to connect this chemical potential to other properties or thermodynamic variables which we can evaluate. So, let us consider a phase alpha. Now, phase alpha contains pure solvent. So, I can write here mu 1 alpha is mu alpha pure 1 at temperature Tp, okay, whereas mu 1 beta is mu beta pure 1 at T plus pi, but considering that now this is in a solution, you are going to write RT ln A1. A is the activity which is given as gamma 1 activity coefficient multiplied by composition. Okay. This is something which we have briefly touched upon, but we are going to look into this activity more in detail in very soon in few lectures from now. Okay. So, now this is the important part. Let me just write down, this is equation 1, 2 and 3. Okay. Now, considering the alpha phase is pure, okay, in general what we can do is or in general if you are looking at pure fluids, we can write down this expression del mu by del P at constant temperature is equal to molar volume. This is for pure fluid. Okay. Now, assume incompressible fluid, then I can write down this, I can expand this considering V is equal to constant, then I can write mu pure 1 at, if you integrate this as this would be your P plus pi is equal to mu pure 1 P, and this delta P is nothing but pi V pure 1. Okay. So, this is now expression. Now, I can plug this in equation 3. Therefore, 3 can be written as minus ln A1. If I plug in here, okay, then I get this expression pi V pure 1 divided by RT. Okay. So, this is the expression. Now, I can make use of this expression to simplify. So, by considering dilute solution, where basically the concentration of the solvent is almost close to 1 and the concentration or the mole fraction is almost close to 1 and that for the solute is close to 0. So, in other word, for dilute solution, that means beta phase or dilute solution, x1 is 1. When x1 is 1, so this is beta phase, right? And then basically we are saying this implies that gamma 1 is 1. Okay, in other word, I can write equation 5 will become minus ln x1 is equal to pi v pure 1 by RT. Okay. Now, I am interested in basically in the mole fraction or the x of 2. So, in such case when x1 is 1 or the word when x2 is much less than 1, then ln x1 is equal to ln 1 minus x2, and since x2 is very small, I can write this as x2. So, 6 now can be written as pi v pure 1 is equal to x2 R2. Okay. Now, I can replace this x in terms of the moles also. So, because x2 is much less than 1, this implies that n2 is much less than n1, and we can write x2 as approximate as n2 by n1 because n2 is very small. So, n1 plus n2 here in the denominator can be simply written as n1. So, therefore, pi v pure 1 is nothing but n2 by n1 RT, or pi v is equal to n2 by RT, where v is basically nothing but n1 v pure 1. This is the total volume available to n2 moles. Okay. And this expression is a very famous expression, pi v is equal to n2 by RT, is called Hoff equation, where it connects the osmotic pressure pi to the volume and to the other thermodynamic variables. Okay. Now, if you look at this expression very carefully, then this is analogous to ideal gas equation of state. Okay. But the most important thing is that it all is based on certain assumptions. So, what are the assumptions here? That the solution is very dilute and the solution is incompressible. So, if you look at very carefully this equation, if we measure pi, that means the pressure. So, you can measure the pressure in the left hand side of the membrane and you measure the pressure on the right hand side of the membrane, you can take the difference and you get pi. So, if you can measure pi, if you can measure temperature and as well as the mass concentration of solute, then we should be able to find out the molecular weight of the solute, and this is something which is the very common way to obtain molecular weight of large molecules. So, if you measure pi t and mass concentration gram by L, you can find out molecular weight. Okay. So, this technique to obtain molecular weight for large molecules is called osmometry. This is a standard procedure, okay, for large molecules. So, for those particular large molecules such as protein, polymers, and usually for other colligative properties to evaluate the molecular weight such as boiling point and freezing point, let us say depression, if those are difficult, then this is an approach to obtain the molecular weight. Okay. Okay, now there are a few points which we must make. One of the important thing is that if you look at this Hoff equation, then this is a limiting case. Okay, it works only for the dilute conditions. What about if the solution is not dilute? Then you have to come up with some other terms which are missing in this equation. So, equation 7 which we wrote here is basically an asymptote that is approached as the concentration of solute goes to 0. So, for the case of finite concentration, what we can do is we can try to write down, instead of saying x2, we can simply say pi by C2 is equal to RT 1 by M2 plus B star C2 plus C star C2 square. The C here is a small c, this is a capital C, okay, where C is, the small c's are the mass concentration in gram per liter, M is molar mass of solute, and B's and C stars are nothing but osmotic virial coefficient. Okay. So, now we have come up with a kind of virial equation state for osmotic pressure. That is what this equation looks like it. Okay. Now, you can recover Hoff equation by putting B star and C star is equal to 0. So, for the case of a dilute solution, we can neglect C star and higher order. So, for dilute solution, if we neglect C star, D star and so forth, and if you plot pi by C2 versus C2, then this, so this part will be your intersection, and this slope, this will give you a slope. That means we can come up with a linear equation having a slope RTB, let us say 2 star, because you are looking at only the B, that means solution or B star, and then intercept is RT by M2. Okay. Now, this B2 star basically is a extremely useful useful information, because it gives you the interaction between the particles in solution, and that is why this is valuable information which you can extract from the experimental data, and you can understand how the solute molecules interact. So, let us consider some example which has been done by by few researchers or workers. So here what I am going to draw is 3 different biomolecules as a function of protein concentration. So what I am going to draw is, so this is pi by C2 as we said in the units of Pascal liter per gram as a function of protein concentration gram per liter. So basically that is what we said, pi by C2 versus C2. So C2 is basically the protein concentration, that means solute here, right? And what we are drawing is basically the case. So I am not going to draw exactly as in the paper of Heinz et al. In 1992 or McCarthy, Adams in 1987. Okay. So I am going to just draw to provide you the basic idea here. So the data are something like this. So this is the case for lysosome, lysosome, okay, and this is around 180, 200, okay, 220, and this is around 69, 49, and this would be the case for so this is your alpha cymotripsine and this is your ovalbumine, okay, and this is around 4, 8, 12, 16, 20. Again these are experimental data, these symbols are experimental data and lines they fit to the experimental data. So what you can see is, given this experimental data and you plotted it, okay, this value, because you know the C2 and you know the pi, so you can plot this expression, okay, that is what we have done or done by these people. So they plotted this lysosome in different solutions. So lysosome was in lysosome and ovalbumine was in 0.06 m cacodylate, okay, and we are talking about pH 5.8, 37 degrees Celsius. For the case of cymotripsine, it is at 0.1 m potassium sulfate buffer, okay, at pH 25 degrees Celsius, okay. Now using this data, so this is a very dilute solution, but using this data you can obtain the slope and the intersection, okay. So if you obtain the slope, you can get B22 and from intercept you can get your molecular weight, and that is what it has been done. So this is the protein. So let us say protein alpha cymotripsine lysosome and ovalbumine. So the B2 is calculated 10⁻⁷ liter mole per gram and molecular weight is calculated, which is something like 32,200 in gram per mole. Okay. What is more important is the value of this B22. Okay, so cymotripsine turns out to be minus 2.72, lysosome is 7.47, 2.76. So what you can clearly see is that the slope is different in the case of lysosome ovalbumine in this solution as opposed to cymotripsine in this potassium sulfate buffer. And having a negative Weyl coefficient indicates that it is effectively attractive to each other, okay, in the solution. Whereas the other one, lysozyme and oval bean, they are not, okay, which is opposite to what you see in chymotrypsin. Now, using this analysis, you could get certain idea of the solute's behavior in solution and as well as molecular weight, and thus this kind of exercise is quite valuable in solution thermodynamics or in general the experiments to evaluate the understanding of the behavior of solute. So, that was my intent for today's lecture, and I hope that you got an idea a bit on the using basic concept of thermodynamics to evaluate understanding of the behavior of solute in solutions. We will take up another topic, and subsequently we will do some examples to appreciate this kind of concepts. So, that will be the end of today's lecture. We will see you in the next lecture.